Can you guys hear me? Yeah, is that good? All right. All right, guys. So it's 12 o'clock. I'm going to go ahead and get started. It's my pleasure to introduce our speaker today, Professor Ana Maria Estrada Gomez, who's coming to us from Purdue University. Professor Estrada Gomez, she got her PhD from Georgia Tech in 2021 and works, I'm going to butch this up, on statistical learning methods for data collection, and I believe you're going to talk a little bit about this today. She's published in top journals like Journal of Graphical and Technometrics and Journal of Graphical Computational Statistics. And without further ado, Professor Estrada, thank you for coming.
Thank you for having me. Yeah, so today I'm going to present the work on online fault detection for high-dimensional data streams under resource constraints. This work would not be possible without my PhD student, so I having him there. He doesn't know he's there. He helped me prepare the slides, but not this one, because I don't think he will like his photo there. But anyway, this is thanks to him. Okay, so motivation for this work. So nowadays, complex systems are continuously monitored by hundreds of sensors, and then they provide a variety of high-dimensional data. And then we could analyze this data for modeling, monitoring, and diagnosis in different systems. So for example, in a forest, we could use drones to detect forest fires as soon as possible to minimize losses. Another example is a power grid, where we want to detect degrading operating state to prevent outages before they happen. And another example is in steel plate manufacturing. We want to be able to detect defective plates so that we don't have downstream failures. And so we want to do monitoring in these different systems, but the truth is, in many cases, we have resource constraint limitations. So for example, if we have a space that we want to monitor, like an agricultural farm or the example of the forest, we might have limited amount of sensors that we can deploy in our area. So one of the questions that we need to answer is, where do we want to deploy our sensors so that we are still able to detect either an anomaly with the water temperature or a forest fire as soon as possible. And then the other thing is we might also have power constraints because, like for example, in the agricultural farm, these sensors are underground and they might run out of batteries. So we need to be smart on when to turn them on and for how long so that we can save battery time. So those are one type of resource constraint that we can observe. We can also have transmission and processing constraints. So for example, in the power grid, you have a lot of different sensors placed all over your power grid, but the problem is you cannot process all the information you're collecting in real time for online monitoring. There's just too much data. And so we would want to decide which data to use at any given point in time to still be able to detect a degrading operating state. And then a different type of resource constraint might be related with labeling. So for fault detection, modern manufacturing increasingly relies on machine learning detectors trained on large volumes of labeled data. But in many cases, you have so many samples collected at high speed by high-dimensional sensors that it's actually infeasible to limit all of the data you collect in real time. So you might also have limited labeling resources. So in this talk, I want to introduce a family of adaptive and active learning strategies for online fault detection that will account for these resource constraints that I just mentioned. So I'll start with the first work, which is an adaptive sampling strategy for real-time anomaly detection with unmanned sensing vehicles. So for this work, the idea is that we have unmanned sensing vehicles, and we want to use them for real-time anomaly detection. So you can use, for example, UAVs for wildfire detection. We could use unmanned water vehicles for oil spill detection, or unmanned ground vehicles for crop disease detection. So actually applications are wide. And so if we want to abstract the problem, in the end we have a grid. So we have I times j variables of interest distributed on a rectangular grid. And then due to resource constraint, we cannot observe every point in our grid in real time. So we need to decide where to send the USVs at each point in time. And in addition, these USVs have movement constraints, so they cannot go from point A to point B if the distance is too long. And then on the other hand, if you have multiple USVs, you need to also coordinate between them so that you're doing efficient monitoring of your space. So then the 3 questions that we wanted to answer with this project were how to use the incomplete data to quickly detect a system change, how to select the locations of the USVs at each point in time, and then how to consider the movement constraints of the USVs. So we summarized this into a research objective, which was we wanted to develop an adaptive sampling strategy for real-time anomaly detection while controlling for the movement cost of the USVs. And there are 4 main challenges. The first one is, like I said, we have incomplete high-dimensional observations. We have spatial and temporal correlations that need to be modeled. We have movement restrictions of the USVs, and we also want to coordinate these USVs. And so in the literature, there is a series of papers on adaptive sampling methodologies. So some of them assume that the sensors are stationary, and then they do adaptive sampling. But the main limitation is that they assume that data can be sampled freely without any cost. And in many cases, like we saw, actually moving the USVs from one point to the other actually has a cost that needs to be incorporated into the model. And then there are a few papers that deal with mobile sensors for monitoring, but they assume IID stationary data, and they also assume independent sensors, so they don't coordinate the movement of the sensors. And then on the other hand, there are papers that deal with mobile sensor coverage, but either they treat the problem as a deterministic problem, so they assume complete data and they assume stationary data, or if they consider a stochastic problem, they still assume that data distribution is fixed and known. So in our case, we want to consider all of these 4 challenges and come up with a methodology to tackle all of them. So this is an overview of our methodology. So we start with data, and this is the full data, but like I said, we have only partial observations because we only have partial sensors. And so what we wanted to do is start with a spatial temporal sequential tensor decomposition that's going to decompose our data into 2 components. A low-rank component that's going to capture the low-rank dimension of our problem, and then a sparse component that's going to capture the outliers or potential anomalies of our problem. And with that, we're going to do 2 things. One is we're going to use our sparse component for monitoring, and we're also going to use information contained in the sparse component for our adaptive sampling strategy. Because if we have some suspicion that there's an anomaly somewhere in their space, we want to use that information to guide the movement of the USVs for the next iteration. So now I'm going to explain kind of all of the different stages of our process. But before, I need to explain what a tensor is. So a tensor is a multidimensional array. So you can think of a vector as a 1D tensor, a matrix as a 2D tensor, and then if you stack several matrices together, you'll get a 3D tensor. In this case, we're dealing with 3D tensors where the first 2 dimensions are spatial, and then the 3rd dimension is time. And just some notation, we're going to call every point xijt, and then we're going to have an additional variable, which is going to be xijt if it's known, and it's going to be 0 otherwise. And because we're mostly interested in monitoring, we don't need to consider all historical data, but just the most recent data. So that's why we're going to work with tensor windows. And in this case, it was a tensor window of size 5. So the most recent information is what we're going to use. Okay? So now I'm going to talk about the decomposition. So like I said, the main idea behind this methodology is we're going to decompose our streaming tensor X into a low-rank component L and a sparse component S. So the first question is, how are we going to represent this low-rank component L? And we decided we're going to use what's called the CP decomposition, where the main idea is you decompose your tensor into a sum of R rank 1 tensors, which is basically the outer product of R vectors over here, and so you end up with 3 factor matrices, 2 of them capturing spatial components of your problem, and then 1 of them capturing the temporal information in your problem. And so in addition to this decomposition, because we know that in many problems we have some temporal patterns that we can exploit, we decided to further decompose our temporal pattern into a trend and then some seasonalities. And so this is how we're going to represent our low rank component. So now here we have the two-factor matrices that we want to learn for spatial characteristics, and then the matrices that we want to learn for the trend and seasonalities. And so this is how our optimization problem looks like. So I'm going to go kind of step by step and explain what each part of the optimization problem does. So the first part is the objective function, where we want to minimize the quadratic loss, meaning we want to learn the best representation for x using our low rank component and our sparse component. Then we are assuming that our outliers are sparse, so that's why we add an L1 penalty to our problem. And then we also have some assumption on the smoothness of the temporal patterns in terms of how the seasonalities look like. And then in terms of constraints, we have one that deals with partial observations. So we want to make sure that whatever we are observing stays the same in our representation. Here is constraint representing the CP decomposition. And then lastly, one that takes into account that temporal decomposition that we also included in our problem. So then we realized that this is a large-scale decomposable optimization problem, so we propose to use ADMM to solve it. So we're going to iteratively learn the different components of our problem. So in the first step, we're going to start by estimating the low-rank component iteratively until convergence. Then in the second stage, we estimate the sparse component using soft thresholding. And then in the third step, we estimate the missing data using Lagrangian multiplier method. And then we keep iterating these steps until convergence. And we actually show that if the multiplier sequence of ADMM are bounded, then this algorithm converges to a local optimum in the limit. And in addition to this, we also proposed an initialization scheme because it is possible that we converge to a bad optimum. And we want to make sure that the algorithm is robust to noises and anomalies. And so that's why, as a first step, we use our temporal estimate to estimate kind of what's going to happen in the next stage. And then we also use a spatial information to get kind of an estimate of our low rank component. And based on this estimate, we can also get an estimate for the sparse component. So we use these two estimates as an initial point for our STD algorithm. So that's how we compute the low rank component and the sparse component. So now I'm going to tell you how we use this information contained in the sparse component for our adaptive sampling strategy. So the main idea is we want to balance between exploration of the space because we want to be able to detect something in an area and we don't know what it is. But also we want to be able to exploit the information that we have from the sparse component. So what we propose is to mix two probability density functions. So one is going to act like random sampling. So the more frequently you visit a variable, then the less probably it is that you'll visit it again. And then for exploitation, what we did is we proposed to use greedy sampling. So we fit an empirical kernel density over our sparse component to sample around those areas that are suspicious. And so we actually proved two things for this adaptive sampling strategy. The first one is that no location in the space is going to be unvisited indefinitely. So it means that you're going to visit every point in the space eventually. So if there's an anomaly there, you will be able to catch it. And then the second property is that once an anomaly occurs and you visit that location, the probability of visiting it again will be non-zero forever. And so it means you will keep visiting that location and eventually decide that there's an anomaly there. And so basically these two properties, what they say is you'll be able to catch the anomalies and detect them. So this is the adaptive sampling strategy, but then the tricky part, and I guess the main difference from the literature is the main idea would be if there's no cost of sampling, then you just choose the index of the n largest values from this probability density function. But because there are actually a cost of moving the vehicles, then we propose to use Voronoi tessellations, because it allowed us to both control the movements of the USVs as well as coordinate their movements. So you can see here, kind of on black and white is the density function. And so ideally, you would want to have more sensors in this area because it's where the chances of having an anomaly are. And then this is the original distribution of your sensors. And so what you want is for them to start moving to this, where the biggest mass is. And so for that, we use the Voronoi tessellation, which updates the center of the partitions. And then once the centers are updated, then the partitions are also updated. And then ideally, you would want to run these Voronoi tessellations until convergence. But the nice thing about it is you can actually stop the algorithm as soon as you reach the maximum distance that a USV can move. And so you won't have optimal solution, but you will move in the best possible way towards it. So that's one thing. And the other thing is because we're working with partitions, there's not going to be ever an overlap between these partitions, which guarantees that the USVs are not going to collide. So that's how we handle the coordination of the USVs. So that's how our adaptive sampling strategy works. And then last thing is talk about the monitoring. So for monitoring, we propose a traditional EWMA control chart where we are going to monitor the non-zero entries in our sparse component, because the idea is if we start having a big change in our sparse component and we start seeing a lot of signals there, then that might highlight that we have an anomaly. So we tried this methodology first on simulated data. So we generated data using Gaussian processes. We also created the temporal pattern and add some Gaussian noise. So this is how our in-control data is going to look like. And then at some point in time, we add some clustered anomalies, and so we get our out-of-control data. So the first thing we did was to try these in a controlled environment. So we actually use Georgia Tech's Robotarium, which is a remotely accessible multi-robot platform. So you can actually send your code, and then the robots would do kind of what you tell them to do, right? So we projected our function here, and then they start moving around. And so you can see at the beginning when there's no anomaly, they are kind of randomly moving around, trying to see if there's something to recognize. And then you'll see now there's an anomaly. And in this case, it's really big, so you can see what happens. You can see now the blue sensors are kind of all moving towards and let me play it again. So they are all moving toward the anomaly because they know that something is going on in that area of the space, right? And then you can also see the control chart where at the beginning things are normal, and then when the anomaly occurs, they start saying that, okay, we actually have something out of control. And then we repeated these kind of with larger scale data sets and many more times to see or evaluate the performance of our method. So we compare with 4 different benchmarks. And so the way to interpret this plot, on the x-axis, you have the amount of noise that's added to the in-control data. And then on the y-axis, you have the average round length, which is telling you how many time steps it took for your algorithm to detect that something was out of control. And so you can see that when the anomaly is really small, then it's harder to detect. But as the anomaly increases, then algorithms detect that something is out of control faster, right? And so you can see here that our proposed algorithm, which is STAS, actually outperforms the benchmarks. And then we also ran a version of our algorithm where we did random sampling. And then here you can see really the advantage of the proposed adaptive sampling strategy that we did. And the main reason why this method is outperforming benchmarks is because it's really modeling the spatial and temporal correlation in the system by using the tensor structure. And then, so the main thing when I told you about the benchmarks is they assume that there's no cost of moving sensors, and that's kind of what we wanted to break, because in many cases there is a cost of moving sensors around. And so this, in this plot you can see the distance that every method moved, and then it's kind of, for benchmarks, because they don't actually move, what we did was estimate a lower bound of their movement based on the coordinates of different measurements. And then for us, it's the actual movement of the USVs. And then ours, it's here. You cannot even, for most of the cases, really see a bar because it's really low in comparison with the benchmarks. And then, I mean, it's expected because that's how we designed the algorithm. And we applied our algorithm for online monitoring of wildfires. So we have data like satellite, shortwave, infrared image. And so we use this as an example of how our methodology could work. So the area of interest was about 100 square kilometers. And data was collected from May 17 to May 20, every 15 minutes. And so here's kind of how the data starts, and then we'll see. So far, they're just moving randomly, and then we start seeing they detect a first fire, and then you'll see there's a bigger one, and then sensors start clustering around that area when the fire is larger. And so we were able to detect the fire faster than the benchmarks, and then based on, I mean, we're using satellite images, not real drones, but based on the computations, the average moving speed of the USVs would be around 5.12 kilometers per hour, and the maximum would be 56 kilometers per hour, which are general, like normal velocities for these consumer drones. So in summary, we proposed ST-STD algorithm to decompose incomplete streaming data collected by USVs into spatial structure and a temporal structure, and also sparse locations suspicious of change. We designed an adaptive sampling strategy for real-time anomaly detection that maximizes change detection capability while coordinating the movement of the USVs and controlling the cost of movement. And then with simulation and case studies, we proved that we outperformed the benchmarks. So that's the first work. Then the second work has a similar flavor, but we actually designed an adaptive sampling strategy for online monitoring of partially observed networks. So there are a few things that change, but the idea is very similar, where you have a system that you want to monitor and you cannot observe every variable of interest in real time. So with ubiquitous implementation of network system, online monitoring of networks has raised increased attention to ensure system stability and safety in modern applications. So one example are power grids, where we want to prevent outages. Another example are cyber physical systems, when we want to detect cyber attacks. Or another example is weather station networks. For example, we will want to detect droughts. And so there are main challenges here is like I said, we have resource constraints. So either because of sensor or power, we have issues with data acquisition or data transmission. And so it means we need to monitor our system under partial observations. And then the second challenge for this system is we have complex interactions because we have a network structure. So in this case, this sensor should be monitored more often because it has more neighbors and it could propagate the anomaly faster than this sensor over here. So how to decide which nodes in the network should be monitored when is the critical question that we want to answer, and then also taking into account that the anomaly can propagate along the structure of our network. So our objective is to develop an adaptive sampling strategy for online monitoring of partially observed spatial temporal network system. So for example, here at time t, we have our network, and we are monitoring two nodes at each point in time, and we have an anomaly that occurs here. And so we start deciding how to move these green squares and which nodes we want to monitor. And then as we're moving, the anomaly is propagating around our network. And then the idea is eventually we want to visit those normal nodes so we can tell that there's something going on and we can raise an alarm. So the final goal is to raise alarm as soon as possible. And so we are assuming that the anomalies can be observed from the node measurements and may propagate along the network topology. So in the literature, there are many works dealing with network monitoring, but usually they assume that there are no resource constraints. So they assume the network is fully observed, and this is not efficient where the data is incomplete. And then we've talked about the different works for adaptive sampling, but the main issue for them is they don't consider the network structure. So they ignore the spatial correlation and also the anomaly propagation in the network. And there's only one work that we found that deals with network monitoring and adaptive sampling by Qian et al. But the issue here is that they ignore temporal correlations first, and then the second thing is they assume in-control and out-of-control data distributions are known, which in many practical applications does not happen. And so in this work, we propose a non-parametric spatial temporal model to capture the correlation within partially observed network systems. And we design a sampling function that balances exploration and exploitation by leveraging the network structure. So we have two stages in the modeling part. The first one is actually offline. So we assume we have historical data, historical in-control data, so we can learn the spatial temporal structure of our data, and then we can use this structure that we learn for online monitoring and sequential sampling. So first I'm going to talk about how we do the modeling part with in-control historical data. So the main assumption is that our data follows a zero-mean Gaussian process with kernel K, and then we have some Gaussian noise. And so what we are going to do is we're going to use a state space model representation of our Gaussian process. So the main assumption is kernel function is separable in time and space. So meaning instead of having a kernel that considers simultaneously space and time, we're going to have one for space and one for time. And then we're also going to assume we have stationary in time. And so the way to think about this is the classical view for Gaussian processes is you're at this location, you want to move to this location. But what we're trying to do with this state space view is we're going to move on the space dimension first and then on the temporal dimension. And this is going to help us for computation because we want to do real-time anomaly detection. So we actually need our algorithm to be fast, and then this state space representation of the Gaussian process is going to help us do that. So the first question we need to answer is how our kernels KS and KT are going to look like. And so for the spatial kernel, the first thing is, in general, people use Euclidean distance, but for a network problem, you might not have access to Euclidean distance between your nodes, and it's not related to the network structure itself. Then most of the work focus on the local structure of your network, and they use shortest path distance to measure the distance between two nodes. So in this example, the shortest path between node 1 and 2 in both scenarios would be 2. But then we realized that this shortest path distance kind of ignores the global structure of the network, because in this case, nodes 1 and 2 are more connected than in this example here. And so we propose to use the resistant distance, which basically views the network as an electrical circuit. And so use the resistance between two nodes when each edge has a unit resistance. So in this example, here the resistance would be 2 because there's only one path between 1 and 2. But in this case, it would be 2/3 because there are 3 paths between 1 and 2. And so we want to use the fact that in this case that these nodes are closer to each other because there are more paths among them. So what we propose is to replace the Euclidean distance by in the radial basis function kernel with the resistance distance. And then we show that if we use this distance, we still have a kernel function. So we can use it as a kernel function for our problem. And then for temporal kernel, we didn't work a lot on that. We decided to use this stationary kernel, but others can be used there depending on the problem. So now that we know how our kernels look like, then our question is, or our task is to estimate the parameters in this model over here. And so for that, we're going to use the maximum likelihood estimation. But the main critical thing here is because we're using Gaussian processes, inverting these matrix not easy because it has q to the cube times t to the cube operations. So the first question is how do we address this problem? And because we decided we're going to use a state space model, then we can actually speed the computation process. So we show that we can actually speed this up to O to the q cubed times t. So this is for the offline modeling. After this, we should have estimates for these 4 parameters over here, and that's what we are going to use for our online monitoring strategy. So this is an overview of how the online monitoring strategy works. So the idea is we have observations from our network, and then from our Gaussian modeling, we also have some predictions. And so we can compare what we are observing versus what we are predicting, which is estimated based on normal conditions. And if the deviations are too high, then we can think that there's an anomaly, and we can use that for monitoring. Then we can also use these to enforce our sampling strategy. Again, if we suspect that something's off, we might want to visit those nodes more often. And then we also need to do some state reconstruction, and then I'll talk about these too. So first, let's talk about online monitoring and sampling. So for online monitoring, in this case, we actually propose to use QSUM control chart. With this, mu would be kind of expected behavior of the system in control conditions, and we are estimating this mu using the Gaussian process. And again, could be tricky because of computational issues, but because we're using state space representation, we actually can use Kalman filtering, and then we get recursive equations that allow us to do this in real time. And then for adaptive sampling, the idea I talked to you about before stays the same. We want to do some random sampling to detect or to visit parts of the network that we haven't visited enough and see if we can find something there. But we also want to exploit information that we have from comparing our prediction with what we are observing. So in terms of random sampling, we're still considering the sampling frequency like we did in the previous work. But here we also consider the importance of the node. So we consider the degree of centrality of each node. And so if the degree of centrality is small, then probably we will visit that node less often, because even if there's an anomaly there, it won't impact a large portion of our network. And then we're also considering the uncertainty from our estimates that we can get from the Gaussian process. So again, we will try to visit uncertain nodes more often than the ones we're more certain about. So that's how we deal with exploration. And then for exploitation, we actually want to exploit the proximity between a node and then the nodes that we have flagged as abnormal based on the comparison between observation and prediction. And so for that, we are actually started thinking about how to measure this proximity. And then we thought, well, the first idea is to use the adjacency matrix, because that's how you know which nodes are directly connected with that particular node. But then what happens with the nodes that are connected to that node using 2 paths? So we consider second-order proximity. And then we realize that if we use the exponential function of the adjacency matrix, we can have like a decaying version of these connections in the network. And so we decided to use these as an exploitation strategy. So that's for the sampling part. And then lastly, one thing to consider is the main issue we have here is, let's say we've visited we're at time t, and then at time t minus 1, we visited this node, so it's easy, we know how they look like. But let's say now we visited this node, and for our modeling process, we actually need to know what st minus 1 looked like, but we didn't visit it, so we don't know. So actually, then we propose to use what we call pseudo-observations coming from our Gaussian process to estimate the value for all of the observations over time. And so that way we can kind of have a visual of the whole network at any given point in time, and we can use that both for adaptive sampling and for monitoring. So again, we tried this methodology on simulations. So we generated a 60-node network using the Barabasi-Albert model. And then we generated the measurements using Gaussian process with this kernel over here. And then we added a shift intensity delta to a randomly chosen node in the network. And then we adopted an independent cascade model for anomaly propagation, which is basically telling you that if you're abnormal at time t, all of your neighbors can be abnormal at time t plus 1 with probability of propagation PA. So this is the network structure, and this is how the time series looks like. And we consider 4 different benchmarks. Actually, 2 of them are kind of ablation studies where we just see what happens if we just do random sampling of the network. Then the other option is what happens if we actually observe every node in the network. Then we compared with the work by Chian et al., which considers adaptive sampling for monitoring networks, and then a traditional adaptive sampling paper that performs well in many scenarios. And here again, we're using the average run length as a comparison metric. And so you can see that our proposed method, it's outperforming the benchmarks, except for the case where you have full observations, which is expected, because if you're observing the whole system, you should be able to detect an anomaly faster than if you have partial observations. And then we have 2 case studies. For the first one, we actually use voltage magnitude from the IEEE 118 bus system. So data are collected from 64 load buses for 336 time epochs. And we use the first 168 time epochs for model learning. And then we actually had an anomaly in one of the edges. And then we were sampling 10% of the nodes at any given point in time. So this is kind of in-control data that we use for model learning. Then this is in-control data that we're monitoring, and then here's where the anomaly occurred. But you can see that to the naked eye, it's actually really hard to know that there's an anomaly up there. But the algorithm is able to detect it. So these are the different control charts for our proposed method and the benchmarks, and then you can see that we detect the anomaly as soon as it happens. Then here is kind of how our sensors are allocated after a few time epochs when the alarm is raised. And you can see most of the sensors are tracking this area because they detect that something is off in this region of the network. And then our second case study is the weather station networks, where we're monitoring the temperatures of the Wabash Heartland Innovation Network. And so we collect data for a certain amount of time, and then we want to detect an increase in temperature. And so here you can see it's kind of more obvious that the temperature has increased for these 2 nodes over here. And so again, we're able to detect that shift faster than the benchmarks because we are considering that network structure, but also kind of temporal information in the problem. And here you can also see how in this case, all of our, we're sampling the nodes all around these 2 defective nodes. So as a summary, we proposed a spatial temporal model to capture correlation within the data and proposed a novel kernel to characterize the relationship between the nodes. We designed a sampling function to balance exploration and exploitation that incorporates the structure of the network and the anomaly propagation mode. And then with simulation and case studies, we show that we outperform the benchmarks. And so the last project is ongoing project. So I'm going to go quickly just based on time. And it's a little bit of a different flavor, but I think related ideas. So this work is on an active learning strategy for online batch fault detection and diagnosis. So here the motivation is, in conventional manufacturing, human-driven process and expert diagnosis, experts cannot label all of the data in real time, okay? And then you remember he made these really funny kind of plots. But anyway, so the point here is the expert says there are too many products and he's not a superhero, so he cannot actually label all of these all of these products in real time. So then the other option is, okay, let's use ML to try to label these products for us. But the issue is ML models need tons of data before they perform well, and so that might be a challenge. So I guess the best way would be to actually have a human in the loop to improve these online diagnoses, right? So then computer will have an idea of which samples are more risky, and then will tell the expert to label those samples. And so the objective here is to develop an active learning strategy to efficiently select a batch of informative samples from streaming data for manual labeling in online fault detection and diagnosis. And so key challenges in manufacturing is, well, we have imbalanced data distribution because in general for manufacturing settings, we want all of our products to be to have no defects, right? So we might not observe these defects in our data, and we have imbalanced data, which is an issue. The other issue is even we might have faults that we haven't seen before. So once they occur, how would we be able to detect them if we've never seen them before? So that's what we call an open set problem. And then lastly, and this happens a lot for active learning, is if you're trying to sample things that look bad, you might collect too many of them and then kind of lose information because everything inside looks alike. So you want to still have some diversity in the samples that you are collecting. And so that's what we call the within batch redundancy, and we would want to reduce that. So in the literature, we have 4 challenges that we're trying to tackle: limited labeling resources, imbalanced data, open set, and redundancy within batch. So for fault detection and diagnosis, there's one stream of works that focus on uncertainty, and so they want to explore the space and then also be able to exploit uncertainty to decide which samples to label. There's another stream of work that focus on diversity, saying that the more diverse samples you get, then the easier you would catch a defect. And then there's other works that focus on exploration. But ideally, we would want to focus on all of these areas. And then in addition, these works for fault detection and diagnosis, they don't consider the redundancy within batch. So we want to include this in our analysis. So our goal is to design an active learning strategy to select and label a batch of samples from unlabeled data streams in real time while dealing with the challenge in manufacturing processes. So our problem formulation is, at each time t, we have features of n unlabeled samples are collected. And then due to labeling constraints, we cannot get labels for all of these samples. We just need to decide which subset of Q samples we're going to label. So here, that's why you have less rows, and then we added the labels. And so we want to use a classifier or a fault detector, and for our work, we proposed any classifier that has this form over here. Because it's flexible, you could use logistic regression or kernel regression or even neural networks. So our focus is not on the classifier, but rather on how to decide which Q samples you are going to label. And so this is our methodology overview. So the idea is you start with n samples, you don't have labels. And so we propose a 2-step sampler. So the first one is a joint exploration sampler that's going to tell you which samples to label, but then we're actually going to have a second sampler that's going to see if maybe some samples here are not as interesting as some of the samples that you have collected in your historical data set, and you might be able to swap some uninformative samples here with some informative samples here, and that's how you get your final new data that you're going to use to inform the fault detector and improve it. So eventually you'll be able to label all of the samples properly. And so I'm going to go very quick over this. But the idea is we have an exploitation sampler where we're going to want to maximize the entropy. And then most papers, and here's where the batch redundancy starts to play a role, most papers just maximize the entropy for each sample separately, but then they end up with samples that are very similar to each other, and so they lose information in certain places of the space. So what we propose is to actually maximize the joint entropy so that will allow us to diversify a little bit which samples we are observing at every point in time. And then we've shown kind of how to efficiently maximize these joint entropy computation. And then on the other hand, for exploration, it is well known that core set sampling will help with this exploration. But what we did in this paper is we actually showed that if we choose specific distance metric and then a specific form for this function that we're using to compute distances, then we can guarantee that we're going to have the coverage of our whole space. So now we have a proposition for exploitation sampler and then proposition for exploration sampler. So the question is how to balance these two. And then we propose to use entropy-based weighting criterion. So that will allow us to balance the weight between exploration and exploitation, kind of in a smarter way that we've been doing, where it's just a constant that we decide on how to balance exploitation, exploration. So that's the first joint exploitation sampler. But then the idea is to have a second layer of sampling when we kind of remove samples that are uninformative, like these ones that were selected from the first sampler, and maybe we add some that we already had that we know are informative from other minority samples. So in this case, we'll add these samples that were in our historical data set, and that will allow us to classify better. And so I'm going to skip the simulations just for the sake of time and go to the case study. So we use this for detecting steel plate faults. So again, in a steel manufacturing plant, you have lots of sensors that are monitoring your manufacturing process. But then, because there's so many different out-of-control things that could happen, you actually need someone to inspect the plates, or even you have to use ultrasound to decide which defect is really there. And so that's why we are using these for steel plate manufacturing. And so we had a data set with many fault types, but we actually decided to keep two to showcase how the algorithm works. So we decided to work on stains and dirtiness. And so the way to interpret these plots is for the first 15 time steps, there's only stain faults. You don't observe dirtiness. And then at time 15, you start observing some dirtiness samples. And so that's why at the beginning, you start learning, your classifier starts learning, and you see over time it improved its performance. And then when you have a new fault type, well, it's going to degrade because it's never seen that before. And so that's why you have this drop over here. But then once they know there's something new, they start learning again, and then performance increases again. And so these are different benchmarks, but you can see overall our method kind of learns faster in terms of classifying these samples. So as a summary, we propose an active learning strategy for online FDD under limited labeling resources. We focus on addressing 3 different challenges: label scarcity, unseen fault types, and then within batch redundancy. And so we propose a bi-level active learning framework where we have an initial joint exploration sampler and then a minority-aware replace sampler. And then we've showed that this method outperforms the benchmarks. And that's it. Thank you.
All right, thank you for the nice presentation. I just had a question, a little bit of detail in the middle of the section that you talked about. You talked about using the resistance distance instead of the shortest path distance, which was kind of a neat idea. I'm just curious: is that distance easy to calculate? How is that calculated?
That's a good question. So it's not hard. There's an algorithm to do it, approximate estimation of it. But yeah, it's not computationally expensive.
Okay, good, cool, thanks.
So nice presentation, Anna. So for the first work, my question is, when you learn the tensor profile background data, do you assume you have a full observation available, or you can learn the tensor using the partial observation?
We assume partial observation. So for that one, we don't consider any in-control historical data.
I see. So you go very fast about the drones, like how you can avoid you can do the coordination and avoid a collision. For that part, I didn't get it. Can you clarify again, why, what kind of idea you can somehow control the moving distance and also avoid the collision? Yeah.
Yes. So let's say at time t, you decided that this was the best sampling that you have for that particular time, right? And then for time t plus 1, you estimate your adaptive sampling density, and then now you have that this is your new density, right? And you would want your sensors to move to this location. So this would be optimal solution. So in order to get to this optimal solution, what we use is this Voronoi tessellation problem. And actually the way to solve this optimization problem is an iterative algorithm where you first find the centroids, then based on the centroids create the partitions. Then once you have the partitions, you re-estimate the centroids and then estimate the partitions again. And eventually it will converge to this optimal solution. But so what we proposed is we don't need to get to the optimal solution, but maybe just something that gets us closer to that optimal solution. And how closer would depend on the movement constraints of your USVs, right? So we start iterating this algorithm, and then at some point you know that one sensor cannot move more because of its constraints. So we actually stop the algorithm here, and that's how we prevent breaking any of our movement constraints. So that's how we handle movement constraints. And then in terms of coordination, the thing is these partitions, they won't overlap. So your sensors would be at the centroids and kind of slowly moving, but they would never collide because they would never go to another partition. And so that's how we manage the coordination. So it's not really like they're talking, but just based on how this algorithm works, it will prevent one USV to go into someone else's partition, and that's how they kind of each stay in their own region.
But I recall when you before you conduct this analysis, you assume the underlying there is like I times J nodes, right? So how this Verona related to the underlying partition? So how
we discretize this to a grid.
Thank you. For the second part of the presentation, the adaptive sampling strategy, do you think it's possible to apply that strategy for cases where the topology of the network is also changing over time, or it's a significant?
That's a good question. But that's something we haven't thought about. So I don't know, maybe I have to think a little bit more, but definitely interesting.
Thank you for your presentation. Can you elaborate a little bit more about what the advantage of using UAVs for the wildfire detection over using the satellite images? Like, since for the UAVs, it may faces a lot of practical issues, like the will be affected by the weather or the GPS accuracy or something. Just curious about what the advantage over the satellite images.
That's a good question. And maybe I will give you a wrong answer because I'm not an expert either, not on USVs or not on satellite images. But what I think is you could use USVs for monitoring smaller spaces that maybe you, like, resolution would be good enough from satellite images. So maybe you could use drones for more localized monitoring and then satellite images for more broad monitoring. That's what I think the advantage is, but again, not an expert.
Well, let's thank the speaker again. Thank you very much for the presentation.
Thank you.